Welcome back to the video lectures, which will be video lecture 11. So, in the last two main lectures, we discussed the differential operational amplifier. In this lecture, we're going to look at an improvement on that, the instrumentation amplifier. So, there's section 9.5.4. Instrumentation op-amp. Okay, so what we had with the differential amp, we said we can change the gain, so we can design the circuit to fit our dynamic needs. For example, if you want a gain of 5 to 200 times, but it would require changing two resistances. So, and it's very important to satisfy our ideal differential amplifier equations that both of those are changed in exactly the same way. So change the two existences and exactly the same way. Okay. Also, we had an input resistance. Ri is equal to R1 plus R3, which is good enough for most intents and purposes, but we can improve on that using the instrumentation amplifier. Okay, so in instrumentation op-amp, we can change the gain by just changing one resistor, or if we make it a potentiometer, just one knob. So it makes it much easier to change the gain dynamically. Also, we have a very high input resistance. Okay, so this sounds like magic. Let's see how we build the circuit to be able to obtain this. Obviously, it's a more complicated solution because we want more degrees of freedom and a higher gain, so we want more from the circuit, so therefore we need to build a more complicated circuit. So, the instrumentation amplifier uses three operational amplifiers. Okay, so it uses a differential amplifier, like we've discussed in the last two lectures. So that should be fairly familiar to you. This output is the out, and these resistances we just pick to be exactly the same value, so we know that that ratio that needs to be equal, that requirement will be satisfied. Okay, over here we have non-inverting with input 1 over there, feedback, like we know. The only difference now is they are connected together using a variable resistor, R1. So this changes, this we haven't seen before. The rest of the circuit should be quite familiar to you, and we have an input here as well. Okay, so this part is just 2 times non-inverting, so both familiar circuits to you, and this part is the difference op-amp that you already know. So the instrumentation op-amp is the combination of all of these. Okay, so it looks quite complicated. Let's look at how we analyze this, and then you'll hopefully understand it better. To make the analysis slightly easier, we're going to define a V output 1 here, so output from that non-inverting op-amp, and we're going to define a V output 2 here from this non-inverting op-amp. Okay. So let's analyze. we're going to do node analysis at this point, which I'm going to call Vx, node analysis at that point, which I'm going to call Vy, and then that will help us to determine Vout1 and Vout2, which will plug into our equations for the ideal difference amplifier, and will give us eventually an equation for Vout. Okay. So at node Vx, doing node analysis, Vx minus Vy, so that is this one over here, Vx minus Vy, current flowing out there, and also Vx minus Vout1. Okay, so that's our equation 1. If we do a node analysis at Vy, we get something similar, Vy minus Vx divided by R1 plus Vy minus Vout2 divided by R2 equal to 0. That's our equation 2. Okay, because we know that these are both non-inverting op-amps, and we can see that they get feedback applied over there and over there. Therefore, we know that this voltage Vx will be equal to our input voltage. That's because of the property of operational amplifiers that these two terminals are forced equal if there's negative feedback. So we can say that Vx is equal to Vi1 and Vy is equal to Vi2. Okay, so this is because of feedback. Okay, so let's put these two into our equations and rearrange it a little bit so we get expression for Vout1 and Vout2. So, out of equation 1, we say Vout1 divided by R2 is equal to Vi1 1 divided by R1 plus 1 divided by R2, as well as minus Vi2 1 divided by R1, that's R. Okay, multiply up with the R2, so that gives us an output. Output 1 equals to Vi1 R2 divided by R1 plus 1 minus Vi2 R2 divided by R1. Okay, you can do the same thing for the other equation. So out of 2, we get Vout2 divided by R2 is equal to, these two look very much the same. You'll see that the Vi1s and Vi2s just swap positions. Okay, in this case also multiply up the R2. So that's Vi2 R2 divided by R1 plus 1 minus Vi1 R2 divided by R1. Okay, so we plug these two into our differential amplifier equations. So for our eventual output voltage, that is our gain, which is R4 divided by R3, multiplied by Vi2 minus Vi1. So this comes from the derivation that we did previously for the ideal differential amplifier. Okay, so let's put in the equations for Vout2 and Vout1. So then we have Vout2, that's Vi2 multiplied by R2 divided by R1 plus 1 minus Vi1 multiplied by R2 divided by R1. Okay, so that's everything of this is VR2, and similarly we have minus VI1 plus VI2 I think there should be a minus sign. Okay, so you can see that with some term multiplied by VI2 multiplied by some term, this minus multiplied by that minus, you see that that becomes a plus. So this term will add to that term. Also, this minus and that minus, those two terms will add together. So that gives us R3 VI2 2 times R2 divided by R1 plus 1 minus VI1 2 times R2 divided by R1 plus 1. Okay, and now you can see this factor here is common to both of those. So it's R4 divided by R3 multiplied by 2 times R2 divided by R1 plus 1 VI2 minus VI1. Okay, so we have our gain here in front, and we have our differential voltage, the difference between the two input voltages. So our gain, and it's still our closed loop differential gain, can be calculated as the output voltage divided by the difference between the two input voltages. So V out is equal to this equation, dividing by the difference between the two input voltages will just give us this bit. So our gain is equal to R4 divided by R3, 2 times R2 divided by R1 plus 1. Okay, so this is the gain starting off with our two input voltages over here, up there and down here. That's the gain to our output voltage. Okay. And one important thing to note is we can change this entire gain by changing the R1 potentiometer. So change gain by only changing R1. And that's what we wanted to have, just one knob to turn. Okay. We'll discuss an example of this in class. Thank you.